In the previous lesson, we identified what waves are. A wave is a disturbance that travels through a medium or through space and transports energy from one location to another without transporting matter. There are three key components that we covered. Waves move energy from one place to another. Waves do not move matter from one place to another. And waves involve the vibration or oscillation of the particles in a medium. We also saw that there are two different types of waves, transverse waves and compression waves. All waves, regardless of their type, move energy. The difference between transverse and compression waves is the direction that the particles oscillate relative to the direction of the wave. In a transverse wave, the particles are moving up and down, but the wave is moving from left to right. And in a compression wave, the particles are moving in the same direction that the wave is traveling. In this lesson, you're going to be learning about the main features of waves that we can use to describe their shape, size, movement, and how much energy they're carrying. So what are some ways we could describe the two waves on the screen? We could describe their height. So the wave on the left is tall, whereas the wave on the right is short. We could describe the length of each wave. So the wave on the left is fairly narrow, but the wave on the right is quite long. We could describe how quickly each wave is oscillating. So the wave on the left has a very fast oscillation, whereas the wave on the right has a very slow oscillation. And we could describe how quickly each of the waves is traveling from left to right. The wave on the left is quite slow, and the wave on the right is quite fast. These descriptions are accurate, but as scientists, we need to be able to measure and put a numerical value to the things that we study. They need to be quantitative rather than qualitative. So let's start going through some of these features of waves. Firstly, on a transverse wave, there's a few parts we can identify. The highest point on a transverse wave is called the crest. The lowest point on a transverse wave is called the trough. So in this image, there are 4 crests and 4 troughs. We can also put in an imaginary center line. This is called the equilibrium position. So before the wave passes through, all the particles would be at rest along that line, and after the wave passes through, they would all return to being at rest in that equilibrium position. A nice example of this is the strings on a guitar. Before it's plucked, the string is in its equilibrium position. And as the vibration in the string and the sound gradually fades away, the string returns to that position. So a crest is the highest point of a wave, the trough is the lowest point, and the equilibrium position is the natural resting spot for whatever the wave is moving through. When we want to describe how tall a wave is, we use the term amplitude. On a transverse wave, amplitude is the vertical distance measured from the center line to the height of one of the crests. The distance from the center line to the trough will be exactly the same. To be a bit more technical, amplitude is the maximum displacement of the particles the wave is traveling through. As they oscillate up and down, the furthest they move away from their equilibrium position is the amplitude of the wave. Now, the taller a wave is, or the greater its amplitude, the more energy that wave will be transferring. And this is fairly intuitive. If you imagine being in the water at the beach, you could comfortably stand still when small, low amplitude waves pass by. But a tall, high amplitude wave would have a lot more energy. So we use the term amplitude to describe the height of a transverse wave. Amplitude can be abbreviated by using an uppercase letter A. And because amplitude is a distance, we use the standard units meters, although sometimes it might be more appropriate to use centimeters or even millimeters. To describe how long a wave is, we use the term wavelength. The simplest way to measure wavelength is to measure the horizontal distance between two successive crests. But in fact, wavelength could be measured between any 2 points of the wave that are at the same part of their up and down oscillation. Any 2 points that are what we'd call in phase. So that could be 2 points that are at a crest, or 2 points that are at a trough, any 2 points on a wave as long as they are in phase. But measuring from crest to crest is much easier, so let's just stick with that. So that's one wavelength, this is 2 wavelengths, and this is 3 wavelengths. So wavelength is the horizontal distance between 2 crests. It's abbreviated using this special Greek symbol, which is called lambda. Wavelength is a measurement of distance, so we use the standard units of meters. A really important characteristic of a wave is how fast its oscillations are. If you compare waves A and B on the screen, you can see that the particles in wave A are oscillating much faster. They're moving up and down faster than those in wave B. This feature is called the wave's frequency. Frequency describes how many oscillations or waves there are each second. So wave A has a high frequency compared to wave B, which has a low frequency. So frequency is the number of oscillations or the number of waves passing each second. It can be abbreviated with the lowercase letter f. We use units called hertz to measure frequency. It's just another way of saying how many times per second. And this was named after a German physicist named Heinrich Rudolf Hertz, who made some very important discoveries about waves. So if one wave was passing each second, that wave would have a frequency of 1 hertz. Or if there was 1,000 waves passing each second, that wave would have a frequency of 1,000 hertz. The frequency of a wave is another factor that determines how much energy it's carrying. It would take a lot less effort or energy to do this exercise at a low frequency than it would to do this exercise at a high frequency. Therefore, the low frequency waves are carrying less energy, and the high frequency waves are carrying more energy. Wave period is a little bit like frequency, but rather than saying how many oscillations there are each second, wave period tells you how long each oscillation takes. So on the screen, wave A has a relatively short period, and wave B has a relatively long period. So a wave period is the time taken for one oscillation or one wave to pass a point. Wave period is abbreviated with a capital letter T, and because it's a measurement of time, we use the standard units of seconds. Wave period is actually the inverse of a wave's frequency, which just means that it's equal to 1 over the wave frequency. Wave speed is how fast a wave is travelling through a medium or through space. If we compare the speed of the 3 waves on the screen, you can see that the wave on the left is the slowest, and the speed of the wave on the right is the fastest. So wave speed is how quickly the wave travels through the medium. It can be abbreviated with the lowercase letter v, and this comes from the word velocity, which has a similar meaning to speed. The standard units that we use for wave speed is meters per second. Alright, to summarize, the crest is the highest point on a transverse wave, and the trough is the lowest point. Amplitude describes the height of the wave from the center line to the crest. Wavelength is the distance between 2 crests. Frequency is the number of oscillations per second. And wave speed is how fast the wave is traveling. In all of those examples, we were looking at transverse waves. But what about compression waves? Well, compression or longitudinal waves have most of the same features as transverse waves. The meaning, the abbreviations, and the units are all the same. Some of the features just look a little bit different. We'll use the example of a compression wave in a slinky to go through these now. So right now this slinky is at rest. It's stretched out and all of the coils are evenly spread apart. You could call this its equilibrium position. Pushing the slinky back and forth creates a compression wave. And as the wave travels from left to right, parts of the slinky are squeezed together and other parts are being stretched apart. The squeezed bits of the wave are called compressions, which is where this type of wave gets its name from. And the stretched out bits are called rarefactions. Amplitude in a compression wave is the maximum distance that the particles are moved from their equilibrium position when the wave passes through. So in the slinky, this is the maximum distance that the coil moves back and forth. Wavelength in a compression wave is simply the distance between two compressions. Frequency in compression waves is the number of oscillations, or the number of waves per second, which is the same as in transverse waves. On the right, the slinky is being pushed back and forth at a faster rate, so it has a higher frequency. And lastly, speed in a compression wave is simply how fast a wave moves through the medium. So in this case, the speed of the wave in the slinky at the bottom is faster than the speed of the wave in the slinky at the top.